Welcome to a new lesson. In this lesson, we'll be finding common factors of polynomials. Before we start with examples, I want to show you a bit of the algebra tiles and explain to you how do they work. Algebra tiles are visual representations of polynomials. For example, this big yellow square has a specific value of x squared. It's represented by x squared. Why is it represented by x squared? It's because all the sides are the same, and this length is referred to as x, unknown length side. When we multiply these sides together, x times x, we get the area of the square, which is x squared. Now let's take a look at this red rectangle. It has the same length as one of the dimensions of the square. That's why it's x. And the length of one of the other dimensions is considered as 1 unit. Therefore, it is 1. It is a different color. Therefore, it is going to be referred to as a negative area versus the yellow one, which is the positive area. So therefore, when we multiply 1 and x, we get the area of x, and since it is red, we'll have it as a negative. So whenever you see a representation of one rectangle, it is an x. If it's red, it will be 1 negative x. Now let's take a look at the small square. Each side has the same length of sides as 1 unit each. 1 times 1 is 1. The area of this square is going to be 1 unit. So whenever you'll see a yellow little square, it's going to be a unit of 1. So let's use this idea of algebra tiles to do a question. So what we're going to do is we're going to write a representation for this polynomial using these algebra tiles. So notice that this big square is represented by x squared, and there are 3 rectangles. So that means we have 3 x's. And since it's red, it's represented by a negative. So it's negative 3x. We also have 1, 2, 3, and 4. 4 little squares. That means we have 4 as a unit. So the whole polynomial will be x squared minus 3x plus 4. So these shapes represent this polynomial. Let's take a look at an example. We're going to be using, in this example, algebra tiles to factor a binomial. What is a binomial? Binomial is a 2-term polynomial. What do you mean by 2 terms? Well, there are 1, 2 terms. 1 and 2 terms. Since we're going to use the algebra tiles, let's take a look at the first one. 6n plus 9. Whether we're using an x or an n, it doesn't matter. It's still a variable. Now again, factoring means that we are trying to find 2 or more factors that multiply to get 6n plus 9. So let's take a look at our algebra tiles. We know that we have 6 rectangles. So let's draw them. But we have to place them so that the length side are next to the long sides, and the short sides are connected next to the short sides. So that means the x's are lined up and the unit 1s are lined up as well. Also, let's include the 9 little units, the 9 little squares. So we have 1, 2, 3, 4, 5, 6, 7, 8, and 9. Notice that we cannot line up the little squares right here simply because we do not know how many of them can fit. Can 4 fit? Can 3 fit? We do not know. That's why they have to be fitted beneath these rectangles. So now the entire area is 6n plus 9. But we're looking for the dimensions of these rectangles. That's what really factoring means. So let's take a look at just the height of this. So we know that the length of this rectangle is x, and we have another x, and a 1, a 1, and a 1. So when we add two x's together, we'll get 2x plus 3. 3 because 1 plus 1 plus 1 is 3. So this is the dimension of this side of the rectangle. What about the bottom dimension? Well, the bottom dimension, we have 1, 1, and 1 units. That means we have a total of 3 units. So this means that if we factor 6n plus 9, we'll get 3 times bracket 2x plus 3 using the algebra tiles. And now we're going to factor without using the algebra tiles. So we know that 6n and 9 have factors. We know this 2 has a factor of 2, 3, and an n. And 9 has a factor of 3 and a 3. So which are common? The 3's are common, so we'll take those factors out, and then what's left? We have a 2 left and an n. So we write those in a bracket, plus, copy down the operation, and we also have a 3 left with the 9. And here's a different way to solve the same question. Now let's solve question B. So we're going to use algebra tiles. We know that we have 4 big squares. And we know that we have also 6 rectangles. We're going to place them so that the length sides are matched up together. So make a bigger rectangle using 6c and 4c. Now we're going to take a look at their dimensions. I'm going to draw this little black lines, and I'm going to show you how long is each line. Well, we know that the length of this side is x, this length of this is x, the length of this is 1, 1, and 1. That means it's 3. And since it's 2x, we'll write as 2c. X or c doesn't matter. Now, what about the length of the other black line? We know that the length of this rectangle is x, or c, and the length of this rectangle is also c. And c plus c is 2 c's. So therefore our answer is 2c bracket times 2c plus 3. Don't forget that it is multiplication. That's what we're looking at. What two values multiply, or polynomials or binomials, multiply to get 6c plus 4c squared. So this method is with the use of algebra tiles. Now what about without algebra tiles? So again, we have 6c plus 4c squared. Let's take out all the factors, 2, 3, and c, of 6c, and all the factors of 4. So we have 2 times 2, and since we have c squared, we have 2c's, like that. So let's identify the common terms, or the common factors. We have a 2 for both sides, and we have a c. So that means that's one of the factors, greatest common factors. So 2c will multiply the remaining bits. The remaining, we have a 3, remaining 2 in the c, and don't forget to copy the positive. And these are our factors. The answer that we had before was 2c times 2c plus 3. There is no order of operation for addition, so we could always add 3 plus 2c or 2c plus 3. It's the same thing. Let's take a look at the next example. In this case, we have a trinomial. We have 1, 2, 3 terms. And let's solve this question using Algebra Tiles. So we have 1, 2, 3, 4, and 5 little rectangles, squares. We have negative 10, that means we have 1 rectangle, 2 rectangles, 3, 4. Let me just continue on. So we have negative 10 rectangles, and we have negative 5 large squares. And what we're trying to do is we're trying to group them equally so that each group has the same number of same type of shapes. So we have one group, we have another group, another group, another group, and last group. And we have 5 of those groups. So that means 5 is a factor. And each group has different types of shapes. It has a 1, a 1. It has negative 2 z's, the 2 rectangles, and has 1 big square. And this is our answer. The factors of 5 minus 10z minus 5z squared is 5 times, bracket, 1 minus 2z minus z squared. So this is done visually. Let's do the same question without the use of Algebra Tiles. Again, we should find all the factors of all our terms. So we have only 5. 5 times 1. 10, we have 2, 5, and a z. 5, we have a 5, and we have 2 z's to multiply. The only common term is a 5, or a greatest common factor is a 5. Don't forget to write a 1, because it's what's often happens is that we forget about the 1 and that whole term disappears. So we bring the 5 out and we recopy everything that's left, with spaces, of course. So we have 1, we have 2z, and we have z squared because of those 2 z's. And now what we do is we copy all of the operations. So we have a negative, and we have this negative as well. So we copy those operations down. And this is the same this is the same answer that we got using the Algebra Tiles. Make sure that you are comfortable using both. Let's take a look at the next, and I believe the last problem. We're going to factor the trinomial, and we're going to verify the factors, that the factors are correct. Actually, I kind of want to go back to the last problem, and I want to show you to this problem right here, and I want to show you how to verify that your problem is correct. This is called, the opposite of factoring is called expansion, or expand. So what we're going to do is we're going to take the answer and we're going to use it to come up with the question itself. And here's how we expand. We take the factor that's outside the bracket and multiply with everything that's inside the bracket. So 5 times 1 is 5 times 1 minus 2z times 5 minus z squared times 5. I'm going to multiply everything outside to everything inside. So 5 times 1 is 5. Negative 2z times 5 is negative 10z. And negative z squared times 5, don't forget that there's actually an invisible 1, so that's negative 1 times 5. We will get negative 5z squared. And notice that it is the same thing as the question. So we have checked it. So it's a check. It does work for us. So this is one way to verify that our answer of, well, this is our answer, is correct. So let's go back to the last example. So with the last example, using Algebra Tiles is almost next to impossible. The reason why is because of the cube and because there are two types of variables, x and y's. So we're not going to be using Algebra Tiles for this question. What we are going to do is find all the possible factors. So let's find all the possible factors. So we have, because we have all these negatives, every term has a negative 1 as a factor. Now the 12 it has a prime factor of 2 times 2 times 3. And it has 3 x's and a y. So again, I didn't have much space, so I'm just going to make sure that I show you the 1 as a factor of 20, negative 1 as a factor of negative 20. If you prime factorize it, you get 2 times 2 times 5. There's 1 x and there's 2 y's. And again, 16, it's 2 times 2 times 2 times 2. And there are 2 x's and 2 y's. And we're going to look around to see what's common about all of these terms. What's the greatest common factor? We know there's a 1, negative 1, for all of these. We know there's a 2, because there's 1 in each term as a factor. There's another 2. And is there a 3? No, because the middle term has no 3s, only has a 5. Is there an x? Yes, there's 1 x. And is there a y that's common to all? Yes, there is. And there's no other things in common because we have only x's left, and there's no x's there, and there is an x there. So that is the only thing that's common to all those. That's the greatest common factor. So let's recopy that greatest common factor of negative 1, and I'm going to use bracket as a multiplication to x and y. So if we bring those together, negative 1 times 2 times 2 is negative 4xy. So this is our greatest common factor. So what's left? I'm going to use a bigger bracket. We have 3 and 2 x's. So we have a 3 and x times x. Notice now everything's positive because we got rid of that negative. What about the middle term? We have plus a 5 and a y. And the last term we have 2 times 2 times x and y. Right there. We're going to close the bracket, and we're going to simplify this. So 3 times x is 2x's, that's 3 times x squared, plus 5y, plus 2 times 2 is 4, and we have x and a y. And here is our answer. Here's our factored form. We're going to try to verify this using, again, the expansion, the opposite of factoring. So we're going to expand, and then we'll see if we get our question. So it is good practice to draw these little arrows. So we'll have first 4xy, I'm going to use brackets, multiplied by 3x squared. Then we're going to multiply the negative 4xy again by 5y, and then multiply it again, 4xy, by 4xy, except that's a negative 4xy. So let's see what we get. Negative 4 times 3 is negative 12. And count how many x's do we have. If there's no exponent, there's an exponent of 1. So there's 1x and there's 2 x's. So 1 plus 2 is 3. So it's x3. And there's 1y. Usually we put it in alphabetical order, x and y, when it comes to variables. Oh, it's not positive. Negative 4 times 5 is negative 20. And x times y. So that means y has one exponent, and there's another exponent, and a y times a y is y squared. So we have x, oh, don't forget the 0 for the 20, so we have the x and y to the power of 2. Now negative 4 times negative 4 is negative 16, and x has an exponent of 1, so is y and y. So x to the power of 1 times x to the power of 1 is x to the power of 2. And y to the power of 1 times 1 to the power of 1 is y to the power of 2. And I'm just going to erase these red lines, these red arrows, to show you that indeed our expansion gives you the same polynomial as the question. Therefore, it is correct. Our answer is still, this is our answer, factored form. So this is the answer. And this is verification at the bottom.